Thanks very much, Andrew. That was a great introduction. Thank you. Yes, as you said, I only joined Atlassian last week. So unfortunately, I won't be fielding any Jira support today. So please hold your complaints. But welcome, everyone, welcome. I appreciate it. It's Saturday morning where you are, isn't it? And it's Saturday night where we are. I say we because I notice there is my best friend Kylie in the list, who's from Wellington, where I am from Auckland. If you know the difference between these cities in New Zealand, the biggest being Wellington is really windy, and Auckland is always beautiful. So I hope Kylie will say hello at some point of time, but let's not impose that on him.
Hello.
Hello.
Hello, I'm Kylie. So it's my daughter's name, not me and my name.
See who's got a haircut today. Perfect. Thanks for saying hello, Kylie.
Cheers.
Awesome. Love your haircut. Let's get started, actually. Well, since I could imagine some of us might want to drink and some of us might be a bit hungover, so I don't want to add to your headache or hold you up any longer. But we start with something pretty dumb, right? Dumb. It's good in programming, right? So like programmers, when we say something, we sometimes mean something different. For example, dumb means good. Stupid means good. So it's 5 = 5 is the big question mark. You're welcome to type your answer in the chat. Of course, that is if you really take me seriously, which you shouldn't. As Adrian said, this should be quite laid back, which is what Kiwis are. Kiwis, as we refer to ourselves in here. Well, as programmers, we know this is not a simple answer, right? Because we know there are different ways to mess up this equation, and 5 in those scenarios might not necessarily be equal to 5. So we need a lot of clarification here, right? So you may ask, is it reference equality? Oh yeah, is it double equals or triple equals? Or is it floating points, right? Is it JavaScript? Is it Kotlin, right? So I guess the correct answer to this question, really, in my opinion, is who wants to know, right? Who wants to know? Are you a floating point? Are you a reference? So with that as a start, I want to bring us. I fought the law, and the law won. Now, these are stories, thoughts, and a bit of a rant from me. As I said, I'm currently with Atlassian, but it's important to note that most of the opinions are my own, they're not of Atlassian. Also, there is a link there to my personal blog. You're welcome to bring some traffic to it. Now, if you're expecting some live performance of this song, which I love, you'd be disappointed because that's not going to happen. Well, secondly, I'm no lawyer. So if you're after some legal advice, you will also be a bit disappointed. Now, thirdly, more relevant, I'm actually no mathematician or physicist, but I will borrow a few laws from mathematics so that I can talk about some interesting observations from my personal experience in software engineering. Now, these observations or illustrations might be inaccurate, sometimes even comical, but my hope is that they will lend us a touch of reality about software engineering, and possibly bring out some of the daily struggles that we have to go through. The content of this talk is quite simple. 11 is my lucky number. So we start by looking at some example laws. We talk about Arsenal, my favorite football club. They're doing pretty poorly for information at this moment. We look at a unit test. Then we get into change detection, which is particularly a front-end thing. Then we look at React. And slowly we touch on immutability. Then we talk about classes and functions. We go back to React again. And I talk about a theorem called CAP. And then we touch on a bit of T, right? It's getting late. And then we circle back to laws again. Now, if you look at this, this doesn't make much sense, right? But hopefully I can string them together for you. So
yeah, you touch football, you touch unit tests, some React front-end, immutability, functional, and some T. Sounds about right.
I'm successful.
Yeah.
Okay, let's look at laws. Now, I felt it's a bit irrelevant to bring up the notion of laws to software engineers, right? Or anybody in software. Because we don't really follow any laws, do we? Like, it's not a daily thing. I mean, a lot of us could say, I don't follow any laws. I was never in trouble. Obviously, nobody's going to arrest me, right? Hopefully not, depending on what we're making. So what are you talking about? Well, first of all, I don't make any laws personally, right? Although I'd love to, you know, it would give me a sense of power if I can make laws. But that's not the case. But the reason that I want to bring up laws is that I feel like real laws, there are actually laws in software engineering that can exist without us knowing. And from the other end, we can actually break these laws without knowing their existence. But we can also suffer the consequences of breaking such laws, believe it or not. I mean, the consequences could be different than getting arrested. I mean, hopefully not. Sometimes just without knowing at all, just like real laws. But I think it's helpful if we try to put a definition to such laws, right? And if I try really, really hard, it would be this line. The laws are guidelines for software behaviors. See, nothing fancy or scary, so you shouldn't get any headache, as I said. And it's kind of warm and fuzzy, right? Guidelines. But I must warn you, right? Behaviors could be good behaviors or bad behaviors. Now, let's take an example, right? There's a strange word, functor, which has two laws, really, and these laws kind of govern mapping. What I mean by mapping. So if we have this function there, that's called map, which takes a function itself that it takes any value of A and convert that to B. And then yet another parameter is a list of A's. And then eventually it would turn a list of A's into a list of B. Now, for that map function, there are two laws already, right? So a simple function, two laws. One is called identity. And the second is called composition. I'll give you just a few seconds to get familiar with these two laws. And I have to admit, they look a bit cryptic. What do you mean exactly, laws? I can't understand them. I'm sure some of us would already understand them. But remember, the first time I look at these, I couldn't make any sense out of them. And if that's the case for any of us, here comes the examples. See, for identity, it just means, for example, if you have an array of 1, 2, and you map them without changing any of it, you should get 1, 2 back, right? There's no magic there. However, if we take an array of 1, 2, and we do nothing with the element, we just return each element truthfully, but somehow we get 3, 4, 5 back. That is not lawful. That's a bad map function. We call that map function unlawful. I hope that makes sense. If that does, we can look at composition, and the green lines, they kind of follow the law. You see, if we take an array of 1, 2, and we map it twice, first, we map them to strings with a toString function. And secondly, we get the length of the string from the first map. They should be the same as mapping them once, but with a function that composes both functions from the line above. So first convert to string and then get the length. So the result should be 1, 1, right? Because both are single digit, and you get a string and you get the length, it should be 1, 1. However, if somehow by using that function we get 5 and 8 back, that's unlawful, right? Something must have gone fishy with that map function. It somehow breaks that composition law. Does that make sense? I'll give you a couple of seconds to look at that. And if you have any questions, please type them out. Okay, looks like we're doing really well. I'll take all the credits, of course. Now, something even a bit more practical, right? So as software engineers, especially those of us working on onion architecture or clean architecture or n-tier architecture, we should have spent quite a big chunk of our time writing mappers, right? So for example, I have this magic mapper. We call it SmartMapper. Of course, it should always implement an interface as in the object-oriented world. Now, what it does is that it's generic. It takes some DTO of type T and it maps to something of type U. Now, if you look at that line, if DTO equals null, somehow this author, this programmer decided they want to be really considerate, right? So if the DTO is null, they want to return a new U. So there's a type constraint up there that U should have a new function, which means it should have a constructor. What do you think about that? This is smart mapper. Now, mind you, this is actually a real life example. Well, of course, slightly refined. Any thoughts? I'm looking at the chat. Okay, without further ado, somehow this map function, or this mapper, is going to be disaster for some of us. In particular, whoever wants to consume that function is going to run into trouble there. Now, if you look at that red bit of code, that's where the problem is. You see it, don't you? So this poor programmer who tried to consume this code is doing very well. They're trying to be very defensive. And they're trying to catch a scenario when the profile from the mapper function is not found, so they can throw an exception. Only reasonable, right? It's good code, in my opinion. But we all know, because we've seen the implementation, this defensive programmer will be awfully disappointed because the profile was never going to be null, right? So they become the victims of some very smart code. And I would say they're not the only victims. The author of that original mapper would also be a victim. I mean, especially if they're in the same room as this consuming programmer. You know, programmers can get quite pissed off sometimes. Right? I could be. And that explains why I want to work remotely, you see. It's to avoid physical harm to myself.
And to the others.
Cool. So I could say this mapper is unlawful, in my opinion. Now, what does that really mean? And what does a lawful mapper look like? I would say it's something like this. It's not smart at all. Right? It just truthfully maps a null value to another null value. It's almost insultingly simple, right? But what's important here is the consumers will not have to worry about any quirks or magic about this map function. It behaves almost according to common sense. Now, if you're still not sure, you can try to break the law in a safe way. Nobody's going to arrest you. By sticking to return a new U, remember, by not returning a null. And you shall see if the implementation should not work with the composition law. It might or might not make sense. But if you're in doubt, please give it a go. And I can assure you, it doesn't make much sense. Again, I didn't invent these laws, right? And smarter people actually talked about this a lot already, you know, such behavior. And one of the most relevant, you call it a law, a rule, as you can see there from Wikipedia, that documents polar really well, which means principle of least astonishment. And we can kind of say that the unlawful implementation there introduces astonishment, right? Because, well, we're expecting a null value. We didn't get one. So we were astonished or surprised. And not all of us like surprises at work, especially of that kind. Now, a point here I want to make is that Polar is great, but it's only good as a general guideline. And if you're looking for specific examples or specific guidelines, then you possibly would be like me. I like the functor definition a lot because it's very specific with its terms and conditions. It's also quite simple. I feel I can follow it without much trouble. So let's have another look at functional. A question from Kylie. There is no object pattern in C#. I guess the writer was introducing that pattern. That was my thought. Thank you. That's a great question. I might as well answer that. So my opinion is, now as a side note, the original pattern that I saw kind of follows the null pattern as well. So we might be talking about more or less the same thing as this slide, with this slide. About all this going back and forth. I think this is more or less the null pattern. I think for specific cases, null pattern could be really useful, but if we have a generic usage, then it would trip people up.
Yeah.
Anyway, I'm not endorsing this SmartMapper at all. I think maybe even when it returns null, it could be a bit too smart for its own good. That
especially
said,
especially if it's not a design or in the system already, and then introducing a new pattern, it could potentially break the law that you just mentioned. Voila.
Yes, that's well put. Thank you very much. Yes, so it's all about meeting the unwritten expectations here. I hope that makes sense. Okay, here's Polar, and there's Functor. A bit more about laws, and try to explain why we want to talk about laws. A valid question to ask is that, well, if laws are that obvious, like the functor laws, they're quite simple, right? They're almost done. If they're that obvious, why do we need to make a law to state it and then even try to enforce it? Well, if you say that, then I might laugh a little because because knowing software engineers, we don't really follow the obvious, right? We're not famous for following the obvious. Well, we should. Sometimes we let opinions cloud our judgment, and sometimes we refuse to see the obvious. In my opinion, this is quite a terrible problem we're facing. Right? Everything can be subjective. Everything can be right. Everything can be wrong as well. So in my opinion, I could use some very specific, very unequivocal, unambiguous laws to state the obvious so I can safely follow and know that things will just work. But even better, if everybody kind of agrees that these things are good, so we can follow together, so we don't surprise each other. So here comes the point about the laws. I think laws are quite harmless and they're quite helpful because they state the obvious. They should be good common ground for us. And most importantly, they should keep us honest because, as I said, software engineers are famous for getting quite opinionated. And sometimes we want to ignore the obvious. Now we've seen functor. Let's move on to something else that's even simpler. That's equality. Okay. So here I borrowed 3 of the many laws of equality from mathematics. If you read through them, you find they're super straightforward, right? They have very specific names. There's identity, reflexivity, symmetry, and associativity, all these things, but we don't have to, they're quite straightforward. We don't have to worry about these terms. Now, even these laws are quite complex to me. I beg your pardon. And I want to talk about something that is even simpler. And what is that? I hope you agree, this is quite dumb, right? So if A equal B, then A must equal B. This is like repetition, right? It's tautology. Doesn't really, it's dumb, right? It's really dumb. Do you agree?
Yeah.
Great, thank you. I mean, if you want to have a laugh, or you want to get a bit angry with me, that's fine, because you don't understand. You think, what is this guy talking about? This is a waste of my time, right? But of course, the sharp-eyed of us will say, well, Hackle, you want to talk about strange things like, in SQL, there, null is not equal to null, right? But null is also not equal to null. It's a strange things. Or like you talk about floating points and all these things. No, I'm not going to be talking about these things, right? Very, very common things. Right? If A equals B, then A must equal B. So I admit this might not make the most sense, but I will show an example because I think that would make more sense. So there you go. What do you think? I'll let you read the code, of course. What do you think the answer is here from the console output? So we have person, and we change his name. But before that, we assign it to person B.
Who's asking? I'm using your first slide. I mean, that's what you recommended, right?
Yeah, who's asking? Nice.
So good. In C#, the answer is no, they're not the same. Unfortunately.
Okay. It's not straightforward, right? This is not good. Yeah. This is not a good thing. Yeah, it's not a good thing. It's why should it be so confusing? But okay, let me spoil the fun here, right? You can have a play yourself later. So this is actually depending on the definition of person. So if the person type is a struct, now hopefully you used C# and Java or similar languages. Otherwise, this might be more confusing. So struct is a value type, right? So if person is defined as a struct, a value type, then this would be false because person B is copied from person A before person A changes. It's be false. But if person is defined as a reference type, then the modification also follows, so it would be true. Okay, so let me let's not get all tangled up in the difference between value types and reference type. This is not the point, okay, by far. It's so much for depending on abstraction or implementations, right? We do need to look into the implementation to know what really happens. And personally, I think the mutation here is a bit yucks. But the point I want to bring out here is that, look, it's almost 2022, right? And we're still talking about such quirks as reference types versus value types and, how they're passed around and modified, right? And this still trips us up, right? I mean, trips me up all the time. And you think equality is a fundamental problem should be solved already, right? Like I think that I think we're not in the same realm as mathematicians, where this is it's a never-ending discussion, right? Because it gets really philosophical. If we just deal with values, then why is this still a problem? Right? So it's rather a question. I'm not asking for an answer here. And here's a meme I just made. I'll give you a couple of seconds to appreciate the beauty of this meme. And you can reuse it for free of charge. Okay, so I try to summarize this small law in a similar fashion as the original equality laws, right? So it's, as you say, it's pretty dumb. But I admit, we have to clarify what this means exactly. Otherwise, we can't really go on without a clarification. So let's say on the left side, A equals B or A not equal B. That's what we know, okay? So if we know A equals B, then on the right side, the red text is what we want. You know, we want, or what we get, really. It's what we get, right? So if we know A equals B, then we want to get A equals B, right? Make sense? And if we know A is not equal to B, well, we also want to get from the programming language or from a runtime or from our program that, you know, a result that we're expecting. So if you generalize, this is also polar, right? So there should be no astonishment. Okay, so this is kind of the law. Okay, so I'll be spending a few minutes on. Cool. And still, we're not talking about, you know, null values or floating points, no quirks or, you know, monsters like that. Cool. If you think this is too obvious, you know, too dumb, then I would beg to differ, because I tell you, a lot of web front-end engineers would disagree with us, because these things are not simple at all. I promise I'll talk about Arsenal, the football club that I support, and I'll try to use poor Arsenal as an analogy to the problems that we're facing. Okay, a slight detour. So, you see, Arsenal's not doing very well. They're really poor. Of course, only I can say that, right? So if you're not an Arsenal supporter, you can't say that. Otherwise, we get really upset. They're really poor these days. And one symptom of that is that they're not very predictable with the results of the game. So when that happens, the commentators on TV before the game, you know, they would say something like this: "Oh, let's see which Arsenal team shows up tomorrow." If you think about that, it's a strange statement to make, right? First of all, there's only one Arsenal team, right? I mean, people can say, "Oh, they mean the team selection," you know. But most of the time, you get the same players, you know, the same starting lineup in a team. So I don't think they mean, you know, different players either. What I think they mean is that even for the same players, the same Arsenal, they show up so differently in a game. Their form, it's so ups and downs. There is no reliability. There's no consistency. So you can't really truthfully expect any result. Now, imagine this is quite a source of frustration, right, for fans. You see, how do you deal with this? Because we don't know what to expect. We're talking about, you know, top level league, right? With really good players. They're supposed to be really good players. But they give completely unpredictable results on different days. So how do you deal with this? Well, we don't really deal with it. We just gamble. Right, because we can't predict it. That makes great stuff for gambling. Not that I endorse it, but people do that. But I hope you see the analogy here, right? So software engineering can sometimes feel like Arsenal sometimes, right? When you expect something to do something, they don't. But when you least expect something, you know, it happens. I mean, we won't go as far as gambling on whether a piece of software would work. Right? Maybe we should, right? It would make good games. I mean, some software is so unpredictable, maybe we should put sweepstake on it. I'm giving you business ideas. Okay, so if we apply Arsenal to this simple thing, the simple law that we have, right? When you expect something, you don't get it, when you don't expect it, you do get it. See, Arsenal, it's completely unlawful. Make sense? Okay, we're in the rhythm. Let's let that sink in. Okay, let's look at a unit test. So people usually say, we should always test the behavior, not the implementation. Right? I personally always found that a bit hard to do because how do you define the boundaries between implementation and behavior, right? And there's the questions of granularity and all these things. So it's really, really hard to understand. Well, clearly implementations matter, but sometimes input and output get mangled together. And how does that look like? So we have this test, for he's a jolly good fellow. So we have George, who is celebrating their birthday. And after that, they'll be 1 year older. Poor George. Now, what do you expect this test to do? Would it fail or would it pass? Now, with the previous example, you would have guessed it, right? This is really implementation dependent. Yeah. Well, because it could be one way or the other. I have to place a bet on this. Yeah, it's not good. Now, one implementation could be this, right? Very happy because this person is having a birthday. It's easy. We just increment their age and return the same person. Now, if I get philosophical here, this author kind of believes George is still the same George, just 1 year older. Fair enough. A different implementation is this. Right? And this author thinks differently. Let's say, well, George is now a different person, being a year older. This is where we get a, oh, George, you have changed. And you want to get really philosophical. I should remind us of deep discussions by mathematicians and physicists, right? How the world is integral. But let's not get into that. But if I put it positively, say, this is a good milestone for George. So it's a new person. And it does also the implementation much easier to understand. Well, it makes testing much easier, right? Because now we know the input and output of this celebrate birthday function. They're completely separate things. So I have this ease of mind that this test is absolutely going to pass. So I like this a lot, and we'll talk more about this later. So if we look at reference of this implementation, it kind of breaks the law, right? A simple example, because we know George is a year older. From compare after to before, it's a year older, but the references are still equal. So we get something that we didn't expect. Cool. So we're still using some simple example to test our law, right? So, and you could say, this is like so trivial, right? As engineers, we all know the difference between reference and value types. So you're still not making a lot of sense. Right? Well, I would say the difference between value and value types and reference types, especially with structs, so a complex object can be one or the other. It really muddies the water for me. And it makes things quite blurry. And I don't get the clarity, so I don't get the confidence sometimes. And people can easily break my code by turning a struct into a class or vice versa. And most importantly, I want to stress that, while this is quite basic, I wouldn't underestimate the impact of because next we'll look at something slightly more complex and how things can go pretty wrong. Okay, so in the world of web, we have front-end, back-end, and front-end is quite stateful for its reputation. And people, give front-end quite a lot of sticks, right? So we say, we laugh at them. Used to, not so much these days. We used to laugh at how many front-end works there are and how fast some of them are brought to life and how quickly some of them die. Now, from my observation, one of the fundamental problems of how the frameworks are different or similar can be summarized in, if not one word, one phrase. The difference is how they handle state. Front-end is stateful, so frameworks differ largely by how they manage state. And if we look even closer, then managing state actually has only one core task. And that task is, as the slide says, is about managing equality or inequality. In more specific words, it is the problem of detecting changes, which translate to is A equal to B or is A not equal to B. To me, that's the essential task for managing state. And everything else just follows or is tightly related to this problem. Okay, what is the state problem? Now, if I oversimplify things, it could be summarized as this, right? So you have data, we call it the state, and then you have a view that reflects the data. Now, when the data is changed, something's going to tell the view, hey, the data have changed, please update. Now, from the view, users can change data as well, by giving input or moving their mouse. When that happens, the view says, hey, please change the data because something new is coming in. Okay, it's a simple problem, right? State problem. Now, this might be age revealing. One of the very first solutions to this change detection problem that I can remember, it goes back very far. It's this thing called change notification. I'll give you a few seconds to look at the implementation. So all it does is injecting a function in the setter. This should remind us why setters are so helpful. It kind of works like, wave your hands, just smile and wave. Hey, the value is changed. Please react. Yeah, simple enough. You think this is neat, right? Well, the problem is also quite obvious. We need to inject this into every single setter, right, to enable notifications. It's quite manual, it's quite error-prone. Now, not to mention if we are dealing with types that we don't define ourselves, right? What if there is a class that we don't define? Now we have to create a wrapper to wrap around every single property, every single setter. Now, what if these setters are private? Now, to make it even worse, if we have complex data structures, we also have to account for child properties and grandchild properties. You see my point, right? It's a good idea, but it's very painful to implement. So if you bear with me, all the bells that tries to tell the view to update, it could get really messy. Now, if you think about it, this doesn't follow the law at all. Because change notification basically says, I've got this, to hell with your law, just leave me alone. And I wouldn't say it breaks the law, right? It kind of works around equality. But as we said, it's really, really hard to do all the manual work and to cover all the bases. And they kind of turn programming into hard labor, right? And imagine how people feel about them. So, in my opinion, they never caught on, right? Maybe they're very popular in small areas, but they never became a super popular idea. I have to speed up a little. Now, there's a second solution to change detection, which is called watchers, right? So, for example, we have this. Now we're going to the front-end world. This is TypeScript. We have this data structure called person, which is name agent. There's also address. Now, how do we detect changes? Well, we put a pair of eyes, a watcher, to the age field. Also, address.string. Put another pair of eyes, more eyes, more eyes, more eyes. And if person name changes, this pair of eyes says, gotcha, right? I caught a change. So it's going to tell someone, hey, the name has changed. Please do something. It's a neat idea, isn't it? Well, of course, it's a bit problematic. Well, first of all, it's really creepy, right? You create so many watchers on data fields. That's a joke, but imagine you have more and more watchers attached, and they're external, right? They're not really from within the person type or from each field. They can kind of overlap, right? So it's very hard to keep tab on. You only put one watcher on one field, and you have overlaps, you have conflicts, and when things become really, really tangled, really complex, then you have watchers that never finish watching. They just keep watching, and keep telling the application to update, and then before you know it, it brings your application down to its knees. It's not very desirable. So this also says, to hell with your little law. I've got this. It's kind of like a brute force kind of algorithm, right? It just watches everything. It's a noble attempt. And to be honest, this idea actually had a really good run. You might know what I'm talking about. There's a specific framework that really uses technique to the extreme. They kind of work around the law as well, if we remember the law. But in hindsight, it never would have lasted because you can't work around it, right? It's not very sound, and you run into dead corners if you keep slapping watchers one after the other. Now, this is what brings us to React. Which, in my opinion, kind of champions this idea that changed the horizon of front-end development. Now, people say it's great marketing, but I think it deserves a fair praise. That it's because it really champions this idea of predictable equality. By that I mean unifying reference equality with value equality. Now, what that really means is that if a value changes, also change the reference, and vice versa. So they become one thing. So you can't have a reference change without value change. You can't have a value change without a reference change. Of course, this is enforced by convention, not sometimes with a linter. Okay? And in code, it manifests as spread operators, right? So immutability. But in the end, to summarize, I think it unified reference equality with the value equality. So we have this nice quality with React applications. And guess what that is. If things are not equal, they're not equal. If that makes sense to you now. And in diagram, this is how it works. Okay. So when data changes, instead of updating the old view, React actually conceptually, okay, it's going to create a new view. And when the view has new data to send, new update to send to the state, which updates the state, a new piece of state is created. We're not updating the old state in place. And then, it goes on and on. So nothing is changed in place. So new references keep being created, new views keep being created. It's nice, it's neat. And if we apply our little law to it, this is how it looks. If A equals B, then A equals B. If A is not equal to B, then A is not equal to B. How's that? I mean, we've come this far, right?
Yeah.
Thanks, Eileen. We've come this far to reach this point. I told you it wasn't easy, right? It was obvious, but it wasn't easy. Okay, let's not celebrate yet. But there's a tiny problem there, right? So if you look at, as I said, how do we work with React? You can't do replace update directly, like line 1. You can't say person.name equals args, because no, right? That's not the React way. Instead, you have to spread person and then use a new name there as a person A. It's different. It's different reference. Or in class component, you kind of say set state and you only pass the name. So set state, the function is going to do the legwork for us, which eventually comes to do something quite similar to spreading person. So this kind of requires us to change the way we write our code. I think line 1 is quite intuitive, right? It's quite conventional, and especially for someone with a backend history like myself. And imagine if things get really, really nested, right? Like really deep, complex data structure, we get into the spread hell. And this is sweat, right? It's not really that savory, to be honest. You see how much equality, or inequality is causing us. And you see how hard it is to achieve this seemingly basic requirement, right? It's not easy, right? We know programming is not supposed to be easy, but not this hard. But of course, in the end, React really tries to create order from chaos. And we must endure some hardship. So this is the cost, the price that we pay to get order from this chaos of equality and inequality. Now I feel compelled that I have to touch on classes versus functions. Some of us may not work on cross-paradigm languages, right? Some languages might be completely object-oriented or functional. But some of us, the unfortunate ones, work with languages that are cross-paradigm, such as JavaScript or Scala. And actually, we have a hard choice to make, right? Do we go with classes or functions? And this is a constant debate, right? And if you want to lose a few friends, you should start this debate. But let's say we look at this world of web development, right? This should remind you of something. There's Frontend and Backend. So on the top drawer, we have classes and who's really good at holding state, right? Now we have a function who shines the brightest when it is stateless. Now on the bottom drawer, we have Frontend, who's intrinsically stateful, as we've seen. And the users, usually they're expected to stay for a while. They hang around because, and they don't want to reload the client side, the browser every single time they change anything. Right? So, Be a really terrible experience. Well, the backend is stateless, right? Especially for web, because HTTP or RESTful APIs, they're on their best behaviors when they're stateless. So now, if you have to marry up the top drawers to the bottom drawers, right? What do? Well, programmers come along and say, yeah, this is easy. You hold my beer, I'm going to show you what to do, right? Yay, see? Simple choice. This is the point you should be laughing. Not at me, but laughing with me. Makes perfect sense, right? Let's take a moment to savor this realization. It's quite sarcastic, right? But we'll have more to say about this later. We'll talk about React again. Remember, we put a tiny star asterisk on how the scorecard for React, how it satisfies the law. But there's a problem. And the problem, if I try to summarize, is how can function A be equal to function B? How can function how can one function be equal to another? Well, surprise, surprise, it's equality again, right? So I always somehow manage to bring us back to equality. Well, it turns out this is a really hard problem, right? Because you can't. It's really hard to prove functions are equal. I mean, you can pipe all the input in the world, and then say, for all the input, the output is the same. But that's only a theoretical possibility, right? Because there are an infinite number of input for most functions if we use a normal type system. Now, how this manifests in React is that in the red bit, I'll give you a second to read the code, of course. So imagine, this expensive button is really, really hard to render. Okay, it's very expensive to render. So we try to avoid re-rendering it, right? But somehow, with the way the code is written, there is a small problem there. Because every time to-do, the component is rendered, is also going to recalculate everything within, including the red code, which means a new on-click handler is going to be created. And how React works is that onClick is actually a prop to this expensive button component. And if onClick, the handler, changes, is going to trigger a re-render on expensive button. And we set expensive button is really expensive. We don't want to re-render it, right? It's a conundrum, isn't it? I mean, this is a perfect way to write a handler. It's a lambda. Everybody loves lambda. What do we do? Well, here, React has to take a step back. It had to go old school, right? It uses reference equality. How's that done? Well, first of all, this IncreaseCounter thing can't be an inline lambda as much as we all love it. We have to extract it out into its own function. But that's not enough because every time to-do component renders, it's still going to create a new IncreaseCounter handler. Okay. So what do? We use this thing called UseCallback, which kind of memoizes this handler depending on the set counter value, which says if this set counter value doesn't change, then IncreaseCounter won't change. And you don't have to fully understand this, but the idea is now to maintain function equality, this is the trouble that we have to go through. And do you like this? I personally don't like it, right? I mean, there could be React experts on this. on this call who can explain this really well. But in my opinion, this is very specific knowledge, and I don't feel confident. I have to dig this deep to understand it, right? I mean, there's a lot of assumption here about how this works. It's very specific, and I have to learn so much to understand the performance of a React application. It's kind of off-putting, and in my opinion, it's a bit too magical, right? But let's forget all these things. What is the real problem here? If we sweep away all the noise, I think the arrow kind of points to set counter, right? Because it says if set counter changes, increase counter will change. But now if we remember this, set counter never changes actually, because use state guarantees set counter never changes. Again, this is just React specific knowledge. But again, if something changes, it will have a cascading or knock-on effect. It changes something else because something else depends on it. But you see where we're getting into, right? What we're getting into is this interdependency of equality, that one thing being changed will lead to other things having to change themselves. And then everything falls to pieces, because previously React actually scored a perfect scorecard, right? Now it can't, because we have to, unless we're happy with the introducing things like UseCallback. So who is really to blame here? I mean, I don't know. Maybe we can blame Arsenal, right? Because this is like Arsenal. Things. Why do you always change? Right? Can't you just stay the same, right? Good Lord. So, well, React didn't really do very well in the end. It's a shame. When we know the functions do exactly the same thing. They're not really equal. We get a inequality for functions. Big shame. And if I circle us back to this class function thing, let's say out of these three, I really love immutability. Right? I think this is a game changer. People try to disguise immutability. People try to disguise immutability as mutation. I don't think that's a good. It doesn't. It puts on the front of one thing for another, which I don't really like. It's too magical. But if you read through this, it's pretty clear what React, it's a very popular library, what the choice they have taken, right? They've gone one way. But here, I think I would slightly disagree. I think maybe, I still miss classes a little if I use React. Just a little, not too much, but I still kind of miss it. Now, if you're compelled...
Sorry to disturb. Just to mention, we've hit the 1 hour mark. Just no pressure. Okay. Just mentioning that out, so you know.
Okay. I'll promise I'll finish in the next hour. Okay. I'm joking. I really we're almost there. Okay. Sorry, I lost track of time because I thought I started the slides a bit early, but I'll speed up. Okay. I feel obliged to bring up T, which it's not really T. It's the Elm architecture, which it's cited usually as a source of inspiration for React, especially React with Redux. Okay, look at what Elm says on its official documentation. And I do appreciate how strong and how powerful the statement is, right? They say Elm programs always look something like this. Always, right? What a strong statement there is. And I like that, right? I like strongly opinionated architecture. But if you look at an example of Elm code, it's more or less, I'm sure some of us used Elm before. This is more or less the blueprint that we can kind of use for complex applications as well. And we can go very far without having to deal with quirks or magic. I mean, I kind of feel bad that I have to tie Elm into this thing, you know, of equality, because the problems never manifest with Elm or similar frameworks like Elm. They just never appear to be an issue. But that's, you know, a point to be made. You know, when things are handled properly, you don't see the issues, right? Now, how does Elm manage it? I mean, we don't want to go through the whole architecture, so you know, you can take my word here. And if, you know, Redux is inspired by Elm, it's actually quite similar. It came really, really close to the Elm architecture. Some, you know, in some aspects, it actually makes things a bit better, right? Why does Elm never have to deal with, you know, the quirks that we deal with? Well, in my opinion, there are a few points, right? There's immutability all the way, and immutability all the way, and immutability all the way. That is actually the only trick. I appreciate we traced all the way, you know, from all the quirks and then of, you know, equality to something this simple. But, you know, not that we're here, I hope, you know, this is no big surprise for us. And I do hope we appreciate, you know, if we stick to something very, very simple, we get strong guarantees of nice qualities for our software. Quickly touch on immutability, because now we're, you know, with Elm and their optimization that comes with it. If we go all the way with immutability, then we spot wastes in our code, right? See, for these two people, the address is the same. This is wasteful. What can we do with it? Well, we can actually just keep one address because they're the same, right? And because the address, once it's created, it never changes. Immutability. Hello, right? So we have this strong guarantee that allows us to optimize. Another example is that, what if we have deeply nested data structure, complex data structure, right? And we have to compare them. It's still quite hard, right? So many fields, we have to recursively go through them. Well, maybe not, right? So we already know in C# or other languages, there's this idea of creating a hash code, and then you compare the hash code instead of comparing each field recursively, right? But the big difference here is that if you have immutability as a very strong guarantee, then the hash code only have to be calculated once, not because the value never changes, the hash code never changes. We can be very lazy about it. And on the top level of a complex data structure, well, it's simple. We just compare the hash code because, you know, nothing changes once it's created. So we have this nice guarantee, which enables a lot of optimization. Now, if we apply, you would really expected this, if we apply our small law against it, immutability scores a very good card, right? So everything is as we expected, and we get the good results that we're wanting. Cool. Quickly on CAP, which is a theory that some of us must be very familiar with, and a warning that we cannot always win with CAP, which is the most important, I think. Very briefly, CAP says, out of consistency, petitioning, and availability, you can get 2 at the same time, and 2 at most. Well, it doesn't say. You know, sometimes you get none for really bad architecture, but at most you
really
get 2.
Good to get 2.
So, but in my opinion, this is actually an equality problem. Now, if you bear with me, this is how it goes. So let's say you have 2 databases, A and A1. They start out to be equal, okay? So we have petitioning, We have consistency because they're equal. Now, a change comes along with two deltas, right? And they're transactional. They're one transaction. Now, it happens to A. Now, to be consistent, we have to copy the deltas over, right? So, when delta A is copied over, at this exact moment, you ask database A1 about delta 2. Now, what should A1 do? If you want A1 to give you an answer immediately about delta 2, although it's not copied over yet, okay, remember, if you want an answer immediately, you're preferring availability because you want it to be available. But if you want A1 to wait until delta 2 comes over, it's fully synced, you're preferring consistency. But you see, this, cap gets a lot of love, right? But in my opinion, it's just equality over time. So we're trying to make things equal, but before that is done, if you ask the question, you introduce this cap problem. So out of these three things, you can only take two. Now, in real life, I've actually seen this. So people say, cap, of course, I can get all three of them. So a real life example is that we have two databases and people somehow believe they can sync these two databases two ways. So anything happened to A or A1, they somehow believe they can, keep them in sync. Now, I'm not saying this is not technically possible. I'm sure, somebody could achieve it, but practically, I think it's a recipe for disaster, this design. Well, with that said, let's go back to laws again. Well, I hope with this lengthy presentation, sorry about going over time, I kind of brought out, it's nice to be lawful, to have these laws. From our example, hopefully we're seeing laws give good and strong guarantees. And with these good guarantees, we get nice qualities followed for free, right? For example, comparing complex data structure. But for us as programmers, we kind of form good intuitions, right, by following simple, almost dumb laws. Now, if you remember the functors, there are actually other similar laws that I found really useful, but I won't bore you with these cryptic names. But if you find them, you spend a bit of time, I assure you, they're really, really helpful. And they're not that complex either. But maybe in one word, I think we should stop gambling, embrace the laws, use the laws. They're warm and fuzzy. What do you think we are if we, if we say for programming there is Stone Age and Space Age? Did I change the gauge or move the dial for you? This is a question that I want to leave with you. But I think based on my observation of how we either follow or not follow the laws, I think maybe we're right here. But this is a question that I would leave to you. Well, if there is, there's one note that I would like to end this with. I hope it's a positive one. Maybe both as programming advice and general life advice. We can win with the laws, right? I hope the governments will be happy about this advice. I think there's much to be done to make acceptable, reliable software. And to me, it's comforting to know there are specific laws that I can fall back on. And by sticking to these laws, we find things that most of the time just work. And these things would work for the future if all of us agree that's a good common ground. And I think if we can learn to use the laws instead of fighting them, then there's a lot to be won, not to be lost. Now, thank you so much. Sorry I went over time. yeah, any questions if we have time?
I have one question in chat, Hackle.
Cool.
Adrian is asking if eventual consistency can eventual consistency be described as an equality problem too?
Right, a great question. I think that's more or less CAP, right? Or related. I guess it would be a bit stretched. I was trying to make the point of, equality over time, and I think we can stretch it to describe eventual consistency in that, before things become equal, what do we do, right? That's the hard choice we have to make. Do we want things to be available or do we want to wait? Well, eventual consistency says, well, I just want things to be immediately available. I don't want to wait, right? I think that's the trade-off that we make knowingly. And that's one of the situations we can't really win, right? But again, I hope the slide says that knowing that we can't win it all, that's sometimes just as important as knowing we can. Does that kind of answer your question, Adrian?
Hopefully.
It's a big topic. It's a big topic.
Yeah, so he gave a thumbs up, so it seems that it fits with his question. Okay.